All right, can you hear me?
Yeah, I can hear you, no problem.
And you can see my slides.
Yes.
Great. 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 So thanks for the introduction. You have my name, you have my title. Basically, what I'm going to talk about today is kind of how we go about doing reproducibility in MIR research, so music information retrieval. And it's going to be very kind of first-person autobiographical version of this. So there's going to be some bias and some skew in how I talk about some of these things. Hopefully that doesn't distort your view of it too much. But it's going to be very high level. That's my plan. So to get us started, let's jump way back in the time machine to when I started in MIR. So my first ISMIR conference was 2008 in Philadelphia. And at the time, MIR research was active and machine learning was starting to become a real core component of MIR systems. It was starting to kind of supplant and replace traditional signal processing methods and handcrafted features and all that kind of stuff. But it was very early days. So the way that we would think about reproducibility in MIR back then was essentially you would go knock on the door of the grad student in the lab who came before you. In my case, that was Doug Turnbull in the middle. And I would say, hey, Doug, I need to do this. Do you have any code that does this? And he would say like, yeah, here, let me email you a couple of MATLAB scripts. And then I would get those and I would fiddle with the numbers and change things, run it over my data set that I got from somewhere else, get some result, publish it, off you go. And that's kind of how a lot of this work happened back then. And I think to some extent, we still do a lot of that, but less so now. And hopefully I'll convince you why that's the case. You're probably getting the sense that this doesn't really give you a good foundation for reproducible research if you're just like making copies of copies of copies as multiple students run through a lab, change things as they go. Things diverge and evolve pretty quickly. And each lab was kind of doing this kind of independently of the others. So, I would have the code to generate MFCCs that I got from Doug, who got it from George Sanatakis, who got it from Malcolm Slaney, who Other labs would have a totally independent parallel implementation that they use, and odds are they're not computing exactly the same thing. So when you see it described in a paper, you get different results. That's going to make things pretty difficult, but not impossible. So a couple of other things that were happening in MIR at the time and are still happening. The main one is Murex. So Murex is the Music Information Retrieval Evaluation Exchange. And the idea is you collect a bunch of data on a private server that nobody else has access to. Everybody collects their code, sends it to some brave volunteer. In this case, it was Andy Amon, who used to run this. And he gets it running on that server, runs it over the private data sets. Everybody runs on the same data set, publish the results, and you get this big table of numbers. And we still have Murex, and it still kind of works in that way. And what this gets you is basically, even if you have parallel implementations of different methods, you at least run on a common data set. You have some apples to apples comparisons. The evaluation code is the same. The data sets are basically the same. So you have some common ground. So maybe you don't get full reproducibility, but at least you have some sense of like, are things kind of working or not? And MIR had been working in that fashion for quite a while. This Murex is pretty old at this point. And on the upper left, you can kind of see that's Stephen Downey way in the corner talking about the Murex results for that year. But I think at the time, people were sensing that this can't go on forever. We can't keep working that way. So flash forward a couple of years to ISMIR 2012 in Portugal. And I had just finished my PhD. I was starting a postdoc and I was looking for new things to do. And this is the first year where we had an unconference session where people could just go up to a piece of paper or write down whatever topics they want to organize a short like half-hour or 45-minute session about, get people together and talk about it. And if you look carefully at this slide, I don't know how easy that is to do on Zoom, but you can see a lot of topics here that are a lot of the same things that we talked about today. So, you have source separation evaluation, recommendation. I think there might even be some reproducibility in here, representation learning. Things haven't changed that much in 9 years. But the one that really got my attention was this one at the top. And this was Python and MIR. So as I said, in 2008, pretty much everyone was using MATLAB code or maybe C++. And those are okay, but they're not really great for interoperability. It's hard to make them talk to other tools, especially machine learning packages. So at the time, 2012, scikit-learn was just starting to get on people's radar. We also had new tools like Theano coming out, deep learning frameworks, but all this stuff was in Python, and we didn't in MIR have a good way to use it. So this workshop session was basically about how do we transition from MATLAB, which is kind of closed and proprietary, into an open software ecosystem that can actually make use of the existing open source tools, especially the stuff that was being developed by other communities. And there was a lot of enthusiasm. We had a lot of attendees in this section. You can see a lot of probably familiar faces in this crowd. I'm in there somewhere, much younger. And the discussion went for a little while, and then we all just kind of realized, well, wait a minute, we don't actually have the core signal processing and audio representation tools in Python that we've had in MATLAB. And that's kind of the first thing that you do before you get to any sort of fun machine learning application work. So that focused me and said, like, hey, if you want to have some impact, go build that tool and make it good. And that's kind of where I got started building Librosa and some other tools. And I've basically been doing that ever since. So, if you look at the GitHub changelog on the Librosa package, the first commit to Librosa was like a week after that workshop. So as soon as I got back into the country and kind of got my wits about myself, I started working on it. And then I started working on contributing to other packages to kind of help round out the ecosystem. So we have MIR eval, we have jams, which I'll talk a little bit about later on, and then a bunch of other stuff that you've probably never heard of, but that I use internally to make my life easier. So like data augmentation and data streaming and stuff. So I work on a lot of these open source tools, and I'll try to give you some explanation of like why and what that kind of work looks like and what it means, at least in my research workflow. At the same time, I've also worked on open data sets. Some of this started when I was in grad school. So I was collecting playlist data. So there's the Art of the Mix collection. I worked a little bit on the Million Song Dataset Challenge, the Recommender Systems dataset. Although I didn't do the data collection there, I just helped organize the challenge. And then much later, I got involved in this instrument detection project, made the open mic data set, and I'm currently working on some new stuff, which maybe I'll get to tell you about in the future, but it's still kind of hush-hush. But the reason that I do this probably is obvious to people that signed up for this workshop. None of us really make progress unless we have access to tools and data. We can't, at this point, do it all ourselves. We need to work as a community. And having common infrastructure, by which I mean software and data, makes this easier. To share results, to reproduce other people's work, even just to implement your own stuff. You don't have to do it all from scratch. Additionally, having open tools and open data that anyone can get access to makes it easier for new people to get into the community. And that is really important for maintaining, a healthy research field. If we don't make things open, then we're the only people that get to use it, and eventually we get bored or we, stop doing this work and it dies. And we shouldn't have that happen. So that's why I care about this stuff. So this talk is about reproducibility, and I started off talking about 2008, 2010, 2012, and things have gotten better. And I think of this kind of as analogous to Moore's law in computer hardware. And the cartoon version of Moore's law is that hardware speed doubles every 18 months. That's actually not at all what Moore's law says, but this is often how it's repeated. And I'll go with that for now. There's a complement to Moore's law, which is sometimes called Wirth's law after Nicholas Wirth, or Gates's law, attributed to Bill Gates, but not actually said by him, which is that software speed halves every 18 months. So our hardware is getting faster, our software is getting slower, and these things cancel each other out. And you end up in this kind of cat and mouse game where you're constantly chasing against the other side and no one really makes progress overall, even though incrementally things are changing. I think something similar happens in reproducibility. So my conjecture here, our individual software components actually have gotten better, have improved, have become more reproducible over time. I think that is not controversial. But I think it's also true that the complexity of the problems that we approach and the solutions that we engineer around them have increased to compensate for that. So reproducibility, I think, is not that much easier now than it was 10 years ago, even though the individual components are better. This is a conjecture. If you disagree with this, I would love to talk about it in the panel session later, but this is kind of my premise going forward. So let's talk about what I actually mean by reproducibility. You often see different terms get thrown around and different ways of defining what reproducibility is. I'm going to go back to Claerbout in 1992, has a taxonomy, and there's a bunch of stages in between these two, but I'm going to pick these two, reproducibility and replicability. So according to Claerbout, reproducibility means that the authors provide everything, all of the artifacts, all the software, all the data, everything else that you need, all the instructions that says that you can exactly reproduce the same numbers, with a small grain of salt, as they did in the initial run of the experiment. So that's reproducibility. You have the same artifacts, you get the same results. You can think of this as determinism. The flip side of that is replicability, which means that someone else starting from scratch can get qualitatively the same results, right? So they re-implement the methods, they collect new data that's qualitatively similar to the data that you were analyzing to begin with, and the end results are basically the same. And I think of these as kind of two extremes, right? If it's reproducibility should be somewhat easy to achieve. If your software is deterministic and everything is well behaved, you should get the same numbers out if you run it again. Replicability, I think, is really what we should be striving for, right? That's when you have a really strong, robust result. If it's replicable, someone else redoes it from scratch and they get the same answer, you've done something right. But that's much more difficult. So you can kind of think of these along a continuum, where on the one side you have reproducibility, the other side you have replicability. Reproducibility, I think, is in a sense kind of hard and brittle, not hard in the difficult sense, but hard in the sense that if you change anything along your entire research flow, it goes out the window, right? So if you move from double precision to single precision floating point numbers, your numbers downstream will change. That breaks reproducibility. It really shouldn't, but by the strict definition, it does. Conversely, replicability is a pretty robust and flexible thing. You should be able to change small details and not have a significant change in your outcome. But that's really hard to achieve in practice, right? Most of the results that we have are not that strong. There are small incremental changes that add up, but most of the time you don't have like this kind of gold standard replicability. What I'll say about this is that most of the things that we see when we do replication work are somewhere in between these two, right? We don't build everything from scratch. We're not going to write our own numerical linear algebra routines. We're going to use BLAS or LAPACK or whatever, or something on top of that, NumPy, Julia, pick your favorite language. At some point, there is going to be a crossover where you say, here are the things that are common from the original implementation to my implementation, and here are the things that I'm redoing. So you're kind of, best case, in between these two ends of this continuum. But more likely than not, you're not even on this continuum. I know that I'm not in almost everything I do. I'm like way over here. Some of these things will work and some of them I know are just not going to work. There's randomness involved, there's careful details. If you want to see a good example of why this happens, go take a look at Alexander Gramfor's keynote from the previous session in this, where he talks about why exactly these things are so hard, even when you're trying your best. But we do make a best effort, and things for the most part are pretty good these days. We do have something approaching reproducibility. But it's always a struggle. So let's talk about why reproducibility is a challenge. What do we see in MIR specifically? And what do we need to make things reproducible? So I'm going to break this down into a bunch of ingredients. So the typical thing, at least in the olden times that you'd see, is a description of methods. So by this, I mean the paper, right? You read the paper, it tells you what the researchers did, and ideally that should be enough. If it's a good, strong, robust, replicable result, you should be able to redo it. that's kind of boring. And these days it doesn't really apply. There's too much going on. So next step down is the software infrastructure. And by this, I mean not specifically your code for the experiment or the researcher's code for the experiment, but more the environment around it. So like what version of Python were they using, what version of NumPy, what version of scikit-learn, the stuff that they didn't write, but that they are using to get the results and that their results rest on top of. That part you need to get right if you're gonna have any hope of doing the rest of it. Then of course, there's the part that we all really care deeply about, which is the implementation. So that's your code as the researcher, the thing that you did. That's the thing that matters the most, you would hope. Oftentimes it doesn't, but that's what you hope for. And a lot of reproducibility work kind of stops at this point. It just says like, okay, version control things, put it on GitHub, make it public, and then you're good. But it really is not the case. So we also need to worry about data, right? If you don't have the same data processed in exactly the same way, you're gonna have a bad time here. So we want your data to be open, publicly accessible, and if that's not possible for some reason, we should hope for some kind of qualitatively similar data that we can use instead. This matters more when you have things like personal privacy, recommender systems, things like that. But it comes up in all sorts of situations for all kinds of reasons. Beyond the data, we talk about reproducibility as getting the same answer, but most of the time you don't care about getting all of the same answers, reproducing all of the numbers and all of the tables in a paper. You care about a few of them, right? So which things are you measuring? What do you care about? And what parts are not that important? These are things that you need to define for yourself when you're trying to reproduce someone's work. And finally, you need to worry about how exactly you're comparing things. And this usually involves some kind of statistics. How much variation should you expect? What's close enough when you're comparing your implementation to a previous implementation? These things are kind of unavoidable and often ill-defined, and it's a thing to be aware of. So these, to me, are the main ingredients. They're probably more than I'm leaving off, but these are the things that I care about. But let's talk about why this is hard in MIR. Specifically, everything that I have here kind of, this applies very broadly to pretty much any computational discipline. In MIR, we have relatively complex pipelines. And one thing, if you're really curious about this, we have a paper in Signal Processing Magazine from 2019, I believe, that really goes into kind of all of this stuff. And I'm going to pick a few points out of this paper. But the first thing that I'll say is the methods that we have in MIR at this point are pretty complicated. It used to be that you would have some wave files, you extract some fixed set of features, you put it into a convex machine learning model, you get classifications out and you're done, more or less. And these days, I think that's rarely the case. Oftentimes you have a lot of manipulation of data, which could be partitioning your data into trained test splits. It could be aligning your data to other data sources. It could be some kind of other transformations, other kinds of subsamplings, all sorts of manipulation of the data happens. You'll probably have some sort of front-end signal processing pipeline that extracts some kind of representation. This is the part that I spend a lot of time worrying about. And then you have some machine learning block most of the time. And that at this point is kind of the Wild West, right? You have these incredibly large, difficult to optimize machine learning models that are sensitive to your random initializations, your choice of seed, how long you run gradient descent, what kind of gradient descent you run, all sorts of stuff can mess this stage up. Your models usually aren't convex, so like you're not even getting the same qualitative answer out. If you rerun it, all sorts of stuff goes wrong. And then you're still not done because you have to take the outputs of that model and decode them into something you actually care about. And this stage is sometimes subtle, sometimes not, but it is a stage to worry about. And these pipelines don't show any signs of reducing in complexity anytime soon. And this is kind of what I mean when I say these things are getting more complex to compensate for gains that we might have to any single one of these stages in reproducibility. After that, of course, there's availability of data, right? Do you have the audio or do you only have pre-extracted features? Do you have annotations? If so, how are they stored and how are you processing them? You have user interactions, like what kind of availability of data do you have? That can make MIR work pretty difficult. especially as we get to larger and larger data sets. We talk about things like audio set, YouTube 8 million, those things are hard to copy and hard to replicate. Of course, beyond that, we have the environment, the computational platform, even down to the hardware. Again, Alexander Gramford's talk goes into these details, so I'll skip it here, but these things really do matter and they drive me crazy as a software maintainer, but they matter. One thing that's particular to MIR, I think, is that our problems are very abstract. And what I mean by this is you're taking kind of a dense, difficult to understand low-level representation, usually an audio signal, and you're mapping it to some high-level semantic representation, maybe a classification or a recommendation or something. And there's a lot of kind of room for quantitative error there that would be really hard to detect if you were just looking at the outputs of the system. So we're trying to build these huge mappings between low-level things and high-level things, and anything going wrong along the way, you may or may not notice. You may not know how to notice it. And this makes it really difficult to ensure that your systems work. Finally, this is not specific to MIR, but most machine learning work, I think. The evaluations that we report in papers, the things that we're trying to replicate, you want to get that same accuracy score out. These are usually not reported very well. We're pretty bad at statistics as a field, and I count myself squarely among that. I'm not good at statistics either. But you look at a table of numbers and you see like the average, maybe over one train test split of the data, maybe over multiple. Sometimes if you're lucky, you'll get like a standard deviation, maybe a p-value if that means anything to you. But that's not enough to characterize the actual distribution of scores. Like, what should you expect? These things really, really matter. And we rarely talk about them beyond just saying, oh, we did this and we did a Bonferroni correction here and p-value 0.0049, great. So these things make it difficult as well. So I want to talk about an example just to drive the point home. And probably this is a little redundant for this audience, but I'm going to do it anyway. So in this paper, we cooked up a relatively synthetic, but I think realistic example of what it looks like if you're going to try and replicate somebody's work from a paper. So we're going to pick a specific problem, in this case, onset detection, and I'll read this block to you. So the idea is, say you're reading a paper and you see a description of a method and you want to re-implement it, you want to replicate it. And this block here, which I'll read, so audio was converted to 22 kilohertz mono, and a 2048 point short time Fourier transform was computed with a 64 sample hop. The short time Fourier transform was reduced to 128 mel-bands and magnitudes were compressed by log scaling. And then we computed an onset envelope using threshold of spectral differencing and selected peaks using the method of Buck et al., reference 32. Okay, that's a pretty compact, dense description of a method for onset detection. I think it's representative of the level of detail that you'll find in papers a lot of the time. But even so, if you were to go down and actually re-implement this, you're going to have to make some choices. And there are a lot of details that are left out of this description. So I'll just pick on a few of them here. So the first one, what kind of windowing function did they use in the short time Fourier transform? You could use a Hahn window, you could use a Hamming window, you could use a Kaiser or Blackman-Harris. There's literally dozens of those that you could pick. They never said what they picked, and most of the time people don't mention this, but it matters. How exactly was log compression implemented? Did they use log 1 plus x, or did they use some sort of clipped, thresholded, decibel scaling? That matters. Even how you do spectral differencing. Do you just do like a mp.diff, like a first order difference on the columns of the spectrogram, or do you do something a little bit more sophisticated, like a Savitsky-Golay filter, where you're smoothing the thing first? Oftentimes people ignore these kind of details, and there are many, many more that you could worry about just for this particular example. But I'm going to pick on these three because we can make two choices for each of these and end up with 8 combinations of these choices that give us different systems. And now the question is, do these actually matter? How much change can you expect to see? So I set up this experiment thinking like, okay, there will be like a little bit of difference, but it won't matter too much. The error bars will mostly overlap, but the means will be, pretty close. I ran the experiment on a pretty standard collection of onset detection data, And it was staggering to me how much difference there was. So I won't go into the details of this, but I think you can see just from the error bars that these three choices matter a lot. And they don't matter independently, they matter as combinations, right? So some things that matter in one combination cease to matter in others, right? Like the choice of window, Hamming versus Hahn window, sometimes matters, sometimes doesn't, depending on the other choices. Likewise, the choice in the differencing. The one robust effect that I saw here was that the actual implementation of log scaling really matters for this particular problem. But overall, the mean could be around 0.8 or it could be around 0.4. And this is F measure, so precision recall balanced against each other for detecting node onsets. And that's just huge, right? That's like the difference between a system working and not. And those are three choices in a single system that are relatively simple. And this was a contrived example to fit in a short part of a paper. But a modern system is going to have hundreds of choices like this. And there will be multiple stages of processing. There will be stuff going on inside your deep learning models that are kind of analogous to these choices, like how are you initializing your filters, or using batch normalization or not, like all those kind of things matter. And we rarely talk about them, and they have a huge impact. So what can we do? Hopefully this convinces you, if you weren't already convinced, that a paper is not enough for reproducibility or even replicability. I don't think it ever was, but I think at this point we're pretty sold on the fact that it's not. We really need the code. Code is necessary to make sure that things are actually working the way that people say they do. But I think it's more than that, and I think code is not sufficient. We need common infrastructure, and we need to not reinvent wheels. We need to reuse tools that are already out there rather than replacing them with our own things, just to minimize the moving parts, right? You don't want to have re-implementations of all sorts of stuff if you can use common implementations of things that you think shouldn't matter, and then you can focus on the things that did change. But if you want to have any hope of even knowing whether your system works or not, that's where you need public data. And this is pretty difficult in MIR, because most of the things that we care about, music is often copyrighted, it's difficult to share, it's difficult to get, and that's a huge barrier to entry. So let's transition now to the data end of things. So a lot of this will be inspired by the software end of things, but is also different. And let's talk about what it means to make data in MIR. So this is something I've done a little bit of, not as much as software, I think, but enough to kind of roughly know what I'm talking about. So as engineers, and I think most of us, to some extent, will identify as some kind of engineer, more so than other things we could identify as. We don't get a lot of training in collecting and producing data sets. We kind of learn it on the job, if at all. But other disciplines actually do train people to do this, right? Physical and social scientists, they get training because this is primarily what their job is about, right? You collect data, then you use it to study whatever it is you're studying. And for us, it's kind of an afterthought. We're all about methods, and then we use data to evaluate our methods. But I think that's kind of backwards. But because of this, it's actually really hard to make data, and most people don't do it. And what that means is that if you do create a data set that is widely used, it pays off huge for you. It's hugely rewarding. And this is a mixed bag. So I think of this a lot in terms of, the three artifacts that we can make as researchers. You have methods, by which I mean like algorithms and papers and stuff like that. And those come and go every year, right? Methods, if you're lucky, it'll last, but most of the time they fall out of fashion pretty quickly. Software, if you do it well, can last a little bit longer, but it takes some maintenance and some babysitting. I've been pretty lucky with this on some projects, less lucky with others. But it can last a little bit longer than methods. But data lasts forever, right? Once something's on the internet, it is no longer yours. It is out there. It belongs to the world, and it never dies. And it will rack up citations for you, and that's great. Sometimes the data should die. I don't think I'll mention specific examples of this, but I think if you've been around the MIR field for a little bit, you maybe have some idea of what kind of thing I'm talking about. You see this more in like computer vision, where you have like the faces in the wild data set, where the researchers eventually took it down, but still people use it when they shouldn't because it has really strange quirks to it. Okay, so if you produce a data set, you're in good shape. Things are good, but it is really difficult. It is really time consuming. It's often not rewarded from kind of the academic research. What do I want to say? Not pipeline, but the powers that be that are evaluating your contributions to a field often will not pay attention to data sets or even software. They pay attention to papers and citations. So usually what we do is we circumvent that by saying, I'm going to publish a data set and then attach it to a methods paper. And then people cite the methods paper, and that's how you kind of gauge the impact of that work. But it's, I think, a little bit askew of what should be measured. So, we do kind of get around that. I think that is changing. I think people are learning how to cite and archive data sets in a better way. But one problem with this is that data sets are hard to make, and the timescales are usually longer than we would like for PhD projects, especially in Europe where PhDs go very quickly. So oftentimes it's not grad students that are doing this. Sometimes they are, but often they're not. And grad students are the ones that do most of the work in the field. So there are incentives to not make data sets. But let's say that you are convinced and you think you need to make a data set and you want to contribute it to the field. So what sorts of things do you need to worry about? I'm going to break this down into two categories. First is the methodological issues. So these are things like, what is the data going to be used for? What kind of biases do you think you'll see? How is it going to be collected and annotated? How are you going to train your annotators? What kinds of societal impacts, privacy concerns, et cetera, might you run into? For this, I think Cynthia's keynote actually mentioned some of these issues about validity of your experimental design and things like that. I think those would fall roughly into this category. I would also point you at this paper from 2018 called Data Sheets for Data Sets by Gabriel et al. And this is a really great resource to just run through a checklist of things that you need to think of and document when you're creating a data set. I'm not going to try and summarize it here, but the key idea is to think of your data set in much the same way that you might think of an electronic component in a bigger circuit. You want to document how it was built, what kind of guarantees it makes, what its tolerances are, how it should be used, how it should not be used, what kinds of things people need to worry about. That's what this paper is about. You should definitely read it. It's really, really good. I'm not going to say more about the methodological things because my expertise is more on the practical side. So that's where I'm going to focus. On the practical side, you have all sorts of other things that are a little bit closer to software. So you think about things like, how are you going to encode the data? How are you going to store it? How are you going to archive it, make it available? What kind of processes will you have for implementing corrections, fielding bug reports, things like that. Some of these are also covered in the data sheets for datasets paper, but they do get pretty much into the weeds of the actual application domain pretty quickly. But this is the sort of thing that I worry about a lot. So let's make this a little bit more concrete for an MIR problem. So for me, what does a data set look like? Most of the problems that I care about are of the form, you have audio in and you want to produce some sort of annotations out. Could be something like instrument detection or chord recognition or structure analysis or beat tracking or something. But the point is, audio comes in, some sort of structured annotation comes out. So a data set for evaluating or training a model to do this kind of work will usually be a collection of paired files. So you'll have file 0.wave and file 0.text that has the annotation, and file 1.wave, file 1.text. That's a typo, that should be a 1, not a 2. And so on. So this is one way that you could do it. And then the files are hopefully independent, and then you can just split them up however you like, build your system, evaluate it based on these annotations, and off you go. This is extremely simplified. I think probably obviously if you've been around MIR, things are never this simple. But this is kind of how machine learning people will approach data storage kind of task. But in MIR, we have a lot more structure to worry about. We have things like metadata for the audio. Often you can get away with ignoring this. Sometimes you can't, especially if you have multiple excerpts from a same song, or multiple songs by the same artist. That's metadata that you need to keep track of because it will bias your statistical evaluations. So we need some structure for keeping track of that. Ideally, we should have some sort of provenance for the annotations. Who made it, when, what tools did they use to make it, what guidelines were they following, something like that. Some data sets are better about this than others. A lot of times you'll find this information in the paper, not in the data, but we need it stored somewhere. Sometimes you want to have multiple annotations per example, right? Especially if you have complicated tasks. Structure analysis is a great one, where you will have multiple annotators working on the same audio recording, and they'll produce different outputs, and they're all equally valid in some sense. But this, one file per annotation framework doesn't quite capture that kind of flexibility. We want some sort of data structure that lets us collect multiple annotations per example. And one thing I didn't talk about at all is what does this .text file even contain and how is it structured? So we need some sort of data format. We need some rules to ensure correctness, some ways to check that your data is valid, things like that. These are all, I think, requirements for a data set in MIR. Things to strive for at least. Most data sets don't meet these criteria, but we can make some tools that make this better. So before going into the tools, I just want to talk briefly about some things that I've seen go wrong in published data sets. And these are mostly within the last couple of years. One of these was last week. And I'm not going to name names here. I'm not out to shame anyone. I'm just saying mistakes happen and you need to be aware of that and you need to expect it. So just some things that I've seen. Typos, they happen a lot. A lot of our annotation tools are not built for a specific task, but they're just kind of general purpose, tag audio with a word. And annotators make typos like chorus to Kraus or Horace or whatever. And if you don't catch this sort of thing, you end up with garbage data and incorrect evaluations. Sometimes you'll collect data in one format and then translate it to, CSV or something like that with a script. And if that script has a bug, then you might lose parts of your data before you even get to the analysis stage. This kind of thing happens more often than I think we would like to admit. And especially if that is done by the person preparing the data and they're not careful about tracking errors, then you would never even see it. It takes a lot of digging to find these things. I've seen errors in like date time conversion, which ends up making things like segments with negative durations just because of like time zone issues, strangely enough. I've seen corrupted audio. I even had one example where an audio recording was actually time reversed. And unless you actually go in and listen to the examples, you would never find that stuff. Of course, that's going to give you garbage predictions. I've also seen things where examples that should not have been included in the data set were, and that gives you just kind of meaningless results because the statistics of the data are not what they were claimed to be. And again, these things happen. We should expect them to happen. Nobody's perfect, but we want to have some tools to help us detect and correct for these issues. If you want even more examples of this kind of thing, Bob Sturm's work is a really great resource, digging into the details of specific data sets. He's not shy about pointing to flaws when necessary. But hopefully this gives you a flavor of what kind of things can go wrong and how we can think about correcting ourselves. So when we do this kind of thing, one thing that I want to say, don't make a new format. Please don't make a new format. It's really tempting to just like dump things into a spreadsheet or CSV or something like that, and then have some rules. CSV is not good enough. And if you want to know why, there's this article here. I guess I'll share the slide somehow, or you can Google so you want to write a CSV parser. Parsing comma-separated value files is way more difficult than you think it should be. So just please don't use it. We have better things out there. But more generally, try to use existing data structures and data formats if they exist and suit your problem. Don't make things from scratch if you don't have to. So one example of a data format that you might want to consider is the JAMS format. And I'm going to talk a little bit about this. I did not create this. I sort of swooped in after most of the people who originally developed it kind of got bored of it or had other things to do. But I've, I guess, maintained it for a little while now. It's not perfect. It's got a lot of flaws, but I think it does illustrate some of the things that we should care about and some of the ways that we can think about correcting our data. So this is originally due to Eric Humphrey, Justin Salomon, or Nieto, Johnson Forsyth, Rachel Bittner, and Juan Pablo Bello back in 2014. And I swooped in a year later and made some corrections or changes or other things that I wanted to see. So what is JAMS? It's the JSON annotated music specification. So it's a generic format that's built to contain different kinds of music annotations. And it does a lot of nice things for you. Makes it possible to contain metadata and multiple annotations in a single file. So you can have all kinds of, chord annotations, structure annotations, beat annotations, everything lives in one object along with the metadata, so things can't get lost from each other. That's a convenience thing, but it is actually really helpful in practice. More importantly, it's self-parsing. You never have to write a CSV parser to do this. It's a JSON object. You can load it with anything that speaks JavaScript object notation, which is every modern language. They also made a Python tool that translates this into kind of a nice object hierarchy with some nice API on top of it that makes it easy to work with. So it's self-parsing in some sense, but even more importantly, it's self-validating. So if you have a garbage JAMS data, it will tell you, hey, this doesn't check out. These values are wrong, and you can't load this data. So this is done with JSON schema, which is a way of just saying, here's what data looks like, and here's how it should look. And this is really, really helpful. And even if you don't want to use JAMS, I think it's still worth looking into JSON schema or other kind of object notation schemas when you're creating a data set. So this was developed in 2014. I swooped in a year later and made some changes to it. The main ones I'll talk about are standardizing annotations to a common structure. So we just categorically decided that all annotations will be some metadata and an array of these tuples that all have kind of the same pattern of time, duration, value, and confidence. The idea here is that most of the things we care about in music are labeled intervals, and that interval could span the entire track, or it could be of duration 0, in which case it corresponds to a single event, like an onset or a beat. But this time duration structure lets you capture that. Value and confidence are left open. These can be anything in a kind of blanket JAMS format, but an annotation will also tell you what the namespace of the annotation is. And that's what tells you how to read value and confidence. So different namespaces might be things like chords or beats or structure or tags for the GSAN dataset, or it can get pretty specific. But what they do is they define what constitutes a valid observation in the value field and what constitutes a valid quantity in the confidence field. Most of the time, confidence is left unconstrained, but things like value for chords, we can actually write down a context-free grammar for saying what is a valid chord annotation. And we did that. And JSON actually doesn't support context-free grammars, but it does support regular expressions, and the chord grammar happens to be recursive, and everything works out nicely so that you can make a regular expression. So we did that. It's horrible, it's ugly, but it's done. And now you can validate chord annotations. And if you have a typo, it will tell you, hey, this doesn't check out. You can't use this. On top of that, we built some interfaces to convert to common formats like pandas data frames or labeled interval arrays that you can plug into MI or eval. But the reason that we wanted to standardize all the different formats into kind of this one kind of blanket container is that now you can kind of treat them abstractly. Everything kind of looks and talks the same, at least until you need to go and look at the value, which means that you can write some kind of generic code that can process annotations easily for a lot of the sort of things that we want to do. So, okay, why do I care so much about validation? Most of the errors, at least the ones that I described a couple slides back, not all of them, but most of them actually do arise from improperly formatted data, right? You shouldn't have a negative value for your duration. You shouldn't have a bad string for your chord label, things like that. These are things that we can check syntactically, so why not? More high level, I think of validation as a contract. It says this data checks out, and if you parse it and it validates, you can make assumptions about it, and that simplifies interfaces that you can design for other software components. So if you want to make something that visualizes annotations, or evaluates them, or sonifies them, or whatever it is you want to do, now you can rely on a standard interface rather than having to parse everything slightly differently. That reduces complexity of the code, makes things easier to work with. From an operational standpoint, I think of defining the schema as helping to clarify what the task actually is, right? If you can write down a schema that says, here's what is good and here's what is not good for a value, for example, for an observation, that helps you. That says, okay, now I can go and write guidelines, training materials for my annotators that tells them what they should be doing. I think that's often not taken as seriously as it probably should be. So we do this work, what does it get us? We can automatically validate data. This is also good for model outputs. You know, we think about annotations as coming from humans, but annotations can also come out of models. And if your models all write to a common format, now you don't have to have separate tools for the ground truth annotations and the model outputs. Everything can just speak the same language. And that's really useful. I use this all the time. You can have a simple interface for manipulating annotations. So for example, if you want to excerpt 10 seconds from the middle of a clip, now you can also say, hey, slice that 10 seconds out of the annotations, and they all have the same format, so it's easy to do it, and everything just kind of works. You can also sample things. You can do all sorts of stuff. You can convert between compatible namespaces. So if you have like pitch in Hertz and you want pitch in MIDI or whatever it is, we can do that for you. We can automatically visualize. We can do all sorts of stuff. This makes life so much easier. I found it super useful in my work, but there are definitely some drawbacks to jams, at least currently. So let's talk about those. Things it's not good at: collection management. It's not even in scope, right? It does not manage collections. It manages annotations for one track at a time. And we talked a long time ago about trying to extend it to do collections and just couldn't figure out a nice way to do it. Luckily, Rachel Bittner and Magdalena Fuentes came along and made mirror data, and that does exactly this task in a slightly different way. So definitely check that out if you're not aware of it. It makes collection interfacing a lot easier. And I think there's probably some room for improvement for making jams and mirror data talk to each other. That could make a really powerful data access tool, but work to be done. Second thing, the one file per track model, where we collect all the annotations into a single file. That's not realistic for every use case, especially if you have very large collections, like hundreds of thousands or millions of tracks. This actually creates a resource issue if you have multiple, say, predictors trying to write to the same object. You end up with race conditions or locks, and that slows things down. It's kind of a pain. But it would be easier if you could separate annotations into separate files that were linked by a common ID. You know, we're thinking about ways to get around that, but it's not an easy problem. From the administration standpoint, so for me, revising and updating the schema to account for new task definitions or new things that we want to do, that's really annoyingly detailed, difficult work. And we're long overdue for an update. So if anyone wants to get involved with that project, please reach out to me, because I would love to have some help on that. I haven't touched it in a while. Okay, so I'm kind of running towards the end of my time. I want to end with some practical advice for you, because it's been a lot of me talking about my experience and tools. So I want to give you some things that you can use as a researcher, a software developer, a dataset creator, whatever it happens to be. So as a researcher / user of software, so as a person just publishing your methods, I won't be the first person to say this kind of thing, but keep your code simple. And if possible, use functions instead of classes. If that sounds weird to you, I strongly recommend to go watch Gael Veracruz's 2017 SciPy keynote. There's a link here, or if you Google it, it'll come up. He talks about how kind of SciPy and scikit-learn and all of those things are sort of designed and why they have the kinds of interfaces they do. And it's really carefully thought out, really well presented. And there isn't a paper that goes with it, but it's worth your time to watch. Strongly recommend it. I'm not going to talk about the general kind of software health issues, because that stuff is everywhere, but things that you might not think about. So first of all, be defensive. Think that code will change out from under you. And by this, I mean your environment. So things in NumPy will change. Things in scikit-learn will change. To protect yourself from that, first of all, use a virtual environment or a container or something. I use Conda environments, but you could use Docker or any number of other things for each project that you do. When you do that, pin your versions so you know exactly what version of each tool was used And this is really nicely done in Conda. You just say export your environment to a YAML file. You can save that YAML file in the repository for your project. And now you can reconstitute it somewhere else sometime in the future. And hopefully, I mean, it's hard to ask for more than that. It's not a guarantee, but it's definitely a good start to getting your environment reproducible at least. And just one little thing that I like to do, whenever I submit a paper or I do the final Camera version of a paper, tag the repository. Because odds are you're going to come back and you're going to change things. There'll be bugs. Or someone will want to know, like, hey, what changed from here to here? If you have Git tags on your repository, it's really easy to know what exactly changed at what point. When you're designing your code, always seed your random number generators. Can't stress that enough. There's a really nice tool that just came out a couple months ago called SeedBank. It's by Michael Ekstrand, who's a recommender systems researcher. And this makes it easy to kind of orchestrate your random number generator seeds. Don't rely on ephemeral data structures. If you are making train test splits, save those splits to a file and just load those files up when you need them. It'll make your life easier. As a software/package developer, so this is more kind of my day-to-day role, try to use semantic versioning. You're not going to succeed, but it's a good goal. Semantic versioning says minor changes won't break compatibility, major changes could. And you have a very rigid structure for what software versions mean, O point, X point, Y, things like that. Make it easy to upgrade. So have slow release cycles if you can. Use deprecation cycles if you're going to get rid of functionality so people have time to adapt. If you don't make this easy, people will not upgrade. And then all the work you do will kind of be wasted. If you're releasing software, make a changelog and please include dates when you release versions. That way people can say, I don't know what version I used, but I know I did this experiment at this time because my files are dated as such. This lets them link those two up. Easy thing to do, makes people's lives better. If you can, make things backward compatible. Instead of replacing functionality, add to it and make it possible to change parameters so that you get older stuff. Maintain historical documentation. Keep your documentation built around from older versions because people might be using the old version, not the new one. And if things change, you want them to be able to look up what it was they were doing. Easy stuff. Read the docs does this for you. It's possible to do this in Sphinx if you're making your own doc, but whatever. Last point, as a data collector. So if you're collecting your own data set, first of all, think, do you need a new data set or can you add to an existing data set? If you can add to an existing data set, I strongly recommend that you do so just because it makes everyone's lives easier. Rising tide lifts all ships and all that kind of thing. Document your collection process. Again, here I'll point you to the Gabriel paper, data sheets. Create a schema, validate your data. Make sure that your data actually is good before you put it out in the wild because it's hard to correct things once they're out. But expect that things will go wrong. There will be errors in your data. Plan for it. Have a plan for making corrections and revisions and re-releases of your data. Treat it as if it was software. It can have a version. Why not? If you don't have a plan, then this will catch you off guard. And obviously, you want to make your data public if you can. Put it in some place like Figshare, Zenodo, or whatever. Doesn't really matter where, as long as it's a permanent archive. You will eventually leave your current institution. Oftentimes, your website will disappear and that gets lost. Don't let it disappear. Put it somewhere that will be permanently archived. Okay, that was a lot of me talking. Some closing thoughts. I do think we're in a better state now than we were 9-10 years ago. Certainly in software, I think arguably in data for the most part. But I think it's also true that our systems are more complex, our data sets are larger, and a lot of these things are harder to kind of investigate carefully. So we need to be extra careful. And we can use tools to help us do that job if you know what to look for. So I will stop there. Here's some references, and I'll take any questions you might have, or you can save them for the panel discussion too. So thanks.
Thank you very much, Brian, for this enlightening talk. We are a little bit late, but we can answer a few questions. So you can use the chat box if you want, or you can raise your hand and use a speech. So I see one hand raised. Okay, Christophe, go ahead.
Hi, Brian. Thanks for
Hey.
the nice talk. It was really awesome to have this collected here, and I really appreciate your work in for this reproducibility thing. I have just one. It's more a comment because I'm sure you are aware of this, but on the point that you said, it's generally better to rely on existing code and implement as little as possible. I totally agree with you that that's the best way for reproducibility and minimizing errors and this thing. But I think it somehow competes with the goal of educating PhD students, because there is a lot to re-implementing stuff yourself, both in signal processing basics up to machine learning and creating the data sets, doing the evaluation instead of using near eval and so on. So I think that's somehow challenging to bring these two things together, because you learn so much when re-implementing, and sometimes it's really necessary to understand it. Yeah, so just maybe also an interesting point for the later discussion.
Yeah, thanks. I completely agree with you. I think I would actually flip that around. And if you're trying to teach someone to do these things, use the standard reference as the thing that they are replicating. And that way you can take the same input, run it through the public library, they develop their own version, and you can check, do the answers agree? Then you still get the benefits of teaching them to do that, but they can use the existing tools later on if they want to.
Yeah, sounds like a good idea. Thanks.
Okay, another question. So we have Axel Marmoret, which has a question. Is there a way to have public audio musical data sets without infringing copyright laws and without creating it from scratch? What are the solutions that are used in MIR?
Yeah, that is one of the questions that we need to worry about, right? Like licensing is huge. There are ways to do it, and it kind of depends on what you need to publish, right? So the million song data set is one example of this, where, yeah, the data is public in a sense. You have features, you have metadata, you have all kinds of stuff for a very large collection of music. What you don't have is the audio, unless you know a guy who has a hard drive with all the 7 digital preview clips, which like maybe you do. But it's really not kind of officially part of the data. But that's one model, right? Extract some features from private data set, release the features, and if those are not invertible, you can't reconstruct the audio, then everybody goes home happy, but you are limited to what that representation gets you. The other way to do it is something like acoustic brains, where rather than kind of consolidating the data, you let the data live privately and have different people run the same code, extract features, and upload them. And then everybody has access to the features. And if you have new features that you want, you can redistribute that code, update the acoustic brains model, you get new stuff out. That also gets around some of the copyright issues, but it's, you know, both of them are difficult, especially if you want to change or add data or add features. I don't have great solutions there. I think it's better to work with Creative Commons open music if you can, if that's suitable for your task, and it's not suitable for every task. But you know, things like Free Music Archive, things like Jamendo, they're good resources that I think we could do more with.
Okay, thank you. Let's have a round of applause for Brian.